Hey, today I'm going to build a kit I bought a few weeks ago on eBay. This is a Chem Uno, which is based off of the Chem 1. If you're not familiar with the Chem 1, it was a single board computer by MOS Technology in the late 70s to showcase their 6502 microprocessor. The 6502 was used in many early computers like the Apple I, Apple II, Commodore 64, Atari 2600, and many more. Dave over at Dave's Garage channel actually just made a video on a Chem 1 he has that has a bus backbone and other cards to make the Chem 1 into a functional computer. It's a pretty cool video, so go check that out. The original Chem 1 was much larger due to all the components required to make the computer work, but the interface was on the lower right corner of the board, and that's what this kit replicates. So like a lot of modern vintage computer clones, this kit's based off an Arduino. It actually doesn't require any other components except for a few resistors. The Chem Uno was designed by a guy named Oscar Vermeulen, I believe, who has a nice website with a lot of documentation on how to build and use the Chem, as well as Gerbers and parts if you want to acquire the parts yourself. He also has other replica kits and a lot of other information on vintage computers. I will link the site below as well as the eBay seller I bought this from if you want to get yourself a kit. So let's open this thing up and see what we have. There's a cool white PC board. So it has the button labels on there. There's our digits. I believe the original Chem 1 has 6 digits, and this one has 8 in total. There's some buttons. And there's our little Arduino. It's an Arduino Pro Mini. And there's a couple other components. There's the resistors. And 9-volt socket. We got a power switch. Alright. Let's open this up. So there's a little Arduino. It's supposed to be already programmed, which is good because I've never actually programmed an Arduino before. Though I don't think you need anything special to do it. I think this one doesn't have, well, it obviously doesn't have a USB port. So I think it has UART coming out the side, which is like a TTL version of RS-232, meaning that it's 0 to 5 volts instead of 0 to 12 volts. So if you actually want to plug this into a computer, you have to have a way to convert this over to 12 volts. I think most people use a little board that has a USB plug and then the level shifting IC on it, which I don't have. But I do have a USB to RS-232 device, and I also have some Max 232 ICs which convert from UART to RS-232. So we should be able to make all that work. But that's not required for this to work. It's only required to hook it to the computer for the serial interface, so that you can use it as a terminal. So yeah, let's go ahead and get this one open. And there's that. Kind of think I'm supposed to have another one of these. We might be short one. Well, maybe not. There's only one on there. See, there's actually 2 on here. There's nowhere for it to go, so that one must not get used. Okay. So I have build instructions, which I'll look over, and then we'll start putting this thing together. I'm gonna make the build real quick. I know that's not necessarily interesting to watch, but once we get it together, maybe we can look through and try to figure out how to use this thing. Alright, so the first step is to put all these push button switches, what they call tack switches, we use as the keyboard, into the board. So I think these are going to be a little tricky to line up. Okay, so once you get them in there, they pretty much hold themselves in place. So we can go ahead and install them all, and then we will go back and solder. Alright, so now that I've done all these, kind of have a little bit of a technique, I guess. So make sure your pins aren't bent or anything when you start. See, let's kind of putting the lower ones in and then get the top ones kind of lined up. So that's where I was leaving it before. But if you press it down, the pins will actually form into the shape they need to be to make the button sit flat. So now if you look back, see like that, these two aren't quite sitting flat. So if you press them down hard, the pins will kind of form over. And you can move them back and forth. You can see that one's a little bit to the right. So just kind of force it over. So yeah, that looks pretty good. So I got the soldering iron warmed up, so let's solder these in place. So when I was making the transistor radio video last week, I was complaining about the camera stand being in my way the whole time, and that would have been really frustrating here. But went on eBay and bought an inexpensive camera stand that clamps to the edge of the table, and it is really nice not having that in the way the whole time. Okay, so the next step is to solder in the resistors. It says to solder them in from the back. So there are 2, 4, 6, 8 1K resistors, and there are 2 and then one more, so 3 2K resistors. So there's 8 of these, so I'm guessing that's 1K. So we got, it's like brown, black, black, brown, brown. So that'd be 1 0 0 and then one more 0. So that'd be 1000 or 1K. So that's right. And then these look like, it looks like 4.7K. It's 4701. So that last one's the multiplier, so that'd be one more 0. So 4700. Let's see. It says, okay, so it says the value is not important, anywhere between 2K and 4.7K. So that's the other 3. Alright, so I have this tool here. Let's see if it can use it. Yeah, it might be too small. So the pin spacing's basically the size of the resistor. So you just bend them over right at the resistor. But normally these holes are a little farther apart. So you can use this tool, and it has different spacings, and it allows you to form the leads. You know, so you can get nice formed leads before you stick it in. But when they're real small like this, I usually just put it over the end here. Form it. Let's see if that works. Yeah, it's still a little big. Yeah, I think in this case, since they were trying to make everything small, probably just bend them over. Yeah, that's fine. Except for, of course, I put it in the wrong place. So there. Go ahead and get the rest of these out. Okay, so the documentation suggests to go ahead and put these 6 in and solder them in, because if you put these other 2, these other 4, 5, these other 4 here, and then now the leads would kind of be in the way of each other. So do these and then snip off the excess. Okay, so the next couple steps, it's important to do the order operations correct. So we need to put these in, which are the pins that hold the Arduino in, but we need to make sure we don't install the Arduino yet. And the purpose of these pins, I don't think they actually carry any signals. I think they're just to make sure that you orient the Arduino correctly. And I said before that there was two that was supposed to go there, and in the documentation they have two that go there, but there's no holes for it on this Arduino, so something's obviously changed between the version that's in the documentation and this. But if we solder those in, then that step will be complete. So it looks like he's got all the holes the sides where it holds everything in, which makes it easy to assemble because you don't have parts falling off when you flip the board over. So maybe it makes it a little harder to get the solder to wick down in the hole, but it probably doesn't really matter for something like this. Alright, so that looks pretty good. Now the reason you can't put the Arduino in yet is because we're going to install these displays here, and these pins are actually behind the Arduino, so you wouldn't be able to solder them if the Arduino was in there. So the next step is to put these displays in there. Usually just bend the pins a little bit when you install something to keep it from falling out. See, these do have an orientation. You want the decimal points to be on the bottom. So I've just soldered one pin on each corner just so I can make sure it's seated properly, because once I put solder all the pins in, it'd be pretty difficult to melt them all at once to be able to, manipulate this, but it looks like it's seated properly. The decimals are all on the bottom. Alright, I think we'll finish soldering it in. This is just some flux wash. Just put it on there and rub it around with this brush, and it'll break up the flux. Evaporates really quick. Alright, so the last step is just kind of hold this over the trash can and spray it real good. With the flux off, it gets the rest of any of the flux off. So I'm going to work on getting this Arduino on here. See if I think I have everything pretty much lined up now. I think these pins right here need to bend that way. Finally have it. Okay, so I need to solder those on, but on the website for this, it actually has a 3D model so that you can 3D print this. So I'm wondering if I should put these all the way down and cut the pins off, or if I should lift it up a little bit. Okay, yeah, it looks like it needs to be pushed all the way down, because if it was lifted up on the pins, it wouldn't be exposed there. Okay, so it's pushed all the way down. Everything should be oriented right, because I had those two extra pins there to make sure you didn't put it in backwards. So solder it in. Okay, so we only have a few components left. So I believe what it's saying is we have a switch here. You could put the switch in there if you were using 9 volts, or you could put the switch there if you were using 5 volts. So I think it says the Arduino is okay if you go into the 5 volt input with anywhere from like 3 to 5, and in the 9 volt it's probably good up to around 12 volts, so this would be your regulated input, and that's your not regulated input. But we're going to use this 9-volt plug, so I think we will put it there, and then our red and black wires will go to positive and negative there, like that. Okay, so I'll solder that in. I've only soldered one of the pins because you can see it's not really seated. I didn't have a good way to hold it there, so now I can just put the soldering iron on that one pin I soldered and press up on the switch and it'll seat it. So there. So now it's perfectly seated, and I can solder the other 2 pins. Actually, I wonder if we should run these into the bottom. So where does the 9-volt battery actually go? Like down here? Yeah, so we probably want the wires to come out the bottom. So let's do that. So the red one goes to positive. And the black one to negative. Those look good. Okay, well I'm gonna clean the little bit of flux we just put on this board from the last few things we soldered together, and then we'll figure out how to get it in this box. I guess we'll just power it up and see if it works. Okay, so it's the moment of truth. I believe that's the off position. So we'll plug that up, cut it on. Uh-oh. Oh, okay. That scared me for a second there. So, buttons look like they do things. I don't know how to use this. Press go. Yeah, nothing's going. So I think that this has programs preloaded into memory. So basically we're going to type in memory addresses and then jump to them using a jump command of some sort. And then those programs will run. But right now it's kind of in the there's nothing in memory emulation mode. Kind of how an actual chem would be on startup. So I'll have to look up how to use that. But let's look at this enclosure for a little bit. I'm guessing the 9-volt battery goes there. Yeah, and it's got a little slot for it. So that looks right. And that fits in there. There's also a little cover for it, which is kind of cool. On the picture of this on his website, he had a little like cheat sheet in here with all the commands in it. So I might see if I can find that. I don't know if that's available on his website or if we just have to make one. So what I don't have are screws to screw this down. So let me see if I have something that'll fit that. Alright, so it's in between a number 4 and a number 6 screw. So I assume it's metric. So I don't really have any metric screws. I went into my parts from one of my 3D printers and found this. I don't know what size that is, maybe like 3 millimeters or something. But it fits easily through there. And it doesn't quite go into that hole. So I would say this is probably the intended screw size for it. So I don't know if these are too long, but I'll screw those in. Well, it looks like the holes don't line up very good, so I guess my print shrunk a little more than expected. But anyways, these two are holding in fine for now. We'll have to take them back out anyway to get the serial stuff working. So we'll figure that out later. Alright, that closes. Peel off the plastic. Put it back on. Alright, so we're working. Okay, so I'll go see how we make something work and then I'll come back. Okay, so I've done a quick review of the website on how this thing works. So I know the basics of it. So if you cut it on, So Go runs a program. SST I think puts you in single step mode. AD is address mode and DA is data mode, and then plus goes to the next address. So the way you would do it is, let's say we want to go to address 200. Address 200 already has a program preloaded into this, so we'll look at that. So you press AD and then your address 0200. Of course this is hex. So this side lists the address that you typed in, and this side lists the data that's in that address location. So now if you push plus, it automatically goes to the next address and shows the data in that location. So you can go through your program quickly like that. So let's do it again. Address 0200. So we're back where we started. So now if you press data, so currently in address 200 we have A5. So I press data, and now I can change the value of the data. So instead of A5, let's make it A6. So then we hit plus, and it'll let us change the data the next value, which here's 10, so let's make it 11. So now if we were to hit address again and go to 0200, now the value in 0200 is A6, and if we hit plus to look at the next one, now the value is 11. So just using those few button combinations, you can pretty much program the thing if you know the machine language values to put in there. So, and then if you were to press go, it would run the program, but we've already messed that program up since we've overwritten it. So let's start over and go to address 0200 and let's press go. So you can see stuff change. We're now at address 20A and the value is 00, which I know is the break command, so that's the end of the program. But what happened? So let's restart again and go to address 0200. So we see the first value is A5, so let's write this down because it's a really short program. So we'll say we're at address 200 and we have A5. So then if we go to the next location, let's say it's 201, we have 10. If we go to the next location, it's 202, we have A6, we have 11, 85, 11, 86, 10, and then 0, 0, 0. So that's alright, so these are all hex. And that's obviously 201, 202. Okay, so what did that program do? So I said there was a little cheat sheet. I did find it on the website. It's kind of hard to read on camera though, so I printed out a bigger one. Of course, it's a little pixelated because it's a small image. But let's go through this quickly. So first instruction is A5. So if we find A5 on here, okay, so A5 is LDA ZP. So the standard, so the A stands for the accumulator, which is, there's things inside microprocessors called registers. They're kind of like variables, like in memory locations, but they're inside the processor instead. So first off, they're really fast for the processor to manipulate, but also they're used in the instructions. So you basically copy memory from or copy values from your actual memory locations into your registers, and then you manipulate them using these commands. So LDA says load a value into the A register, which is called the accumulator, and what you pass it as a memory location of where that value you want to copy into the A register is. So this processor has addresses well above 255. You know, it's larger than an 8-bit number, but all we can store in each location are 8-bit numbers, which means that's why there's two M's here, because it's actually would take two 8-bit numbers to tell it where the actual memory address is. But this is A9, the one we have is A5. So you see it says ZP instead. So what ZP is it's the first 255 bytes. You can tell it, as long as the memory location you're interested in is in the first 255 bytes, you can give it a single byte. So it just makes it a quicker instruction. So anyways, A5 says we're going to load the value in this location into the A register. So the value there is the next value in memory, which is 10. So basically we're loading whatever is in location 10 into the A register. So LDA10 is that instruction. And then we have A6, which is the same thing except for it's LDX, so it's loading into the X register. So we're saying LDX, and we're loading whatever's in address 11 into there. And then we have 85, which is right here. So it is store whatever's in the A register into that location. So oops. Oh, we lost our pencil. Into 11, and then 86 is going to be STX, which is going to store whatever's in the X register into the location following, which is 10. And then 0 is just break right here. So the break happens at address 208, but when the program ended, it actually said 2A. I put 10 here, but it's hex. 20A. And that's because whenever you call the break instruction, it automatically increments the program counter location by 2. So by the time we hit this program, this part of the program is the end of it. So what does this do up here? So we have an A register and we have an X register. So we're loading whatever's in address 10 into A, and then we're loading whatever's in address 11 into X, and then we're storing what's in A into 11, and we're storing what's in X into 10. So what we're doing is we're flip-flopping the data in 10 and 11, address 10 and 11. So let's see that work. So we want to go to address 10, and we see the value 10 is actually stored in there. So then if we go to address 11, the value 11 is actually stored in there. So 10 was in 10 and 11 was in 11. So let's go to the start of that program, 0200, and let's hit go. So we're at 20A, 0 in memory, just like we saw before. So now let's go back to address 0010, and now 11's in there. If we increment to the next location, now 10's in there. So it just flip-flopped what was in 10 and 11. So now if we were to run the program again, it should flip-flop them back, right? So if we say address 0200 and then hit go, now we're at 20800, so the program's done. And if we said address 0010, now it's back to 10. If we go to 11, now it's at 11. So what if we put something different in there? So if we go to address 0010 and hit data, let's make it 50. And then we go to 11 and we'll make it 51. So now if we go back to address 0200 and hit run, our program's completed. So now if we go to address 10, now is 51, and 11 is 50, so they flip-flopped. So that's the basics of how to program this thing. There's a lot of instructions. I don't know what they all do yet. There are more programs in memory, but they're intended to be run through a console, through the computer, through the RS-232 port. So we'll need to build the UART to RS-232 board using our MAX232 chip. But this video is getting pretty long, so I think I'm going to go ahead and end it here. So we'll do that in a future video. But thanks for watching.